Recorded is rolling. So it is Friday, October 14th. Some of you guys just turned this page in. Today's the due date, so I'm going to turn these into administration. Maybe you possibly have a space colony panel. If you do, then I will put that together after school. And remember quiz corrections from the dynamics quiz, which is turning right as quarter one was ending. If you want to do quiz corrections, then just make sure to staple those to your original quiz because I don't have access to your original quiz grades. Okay. All right. So yesterday we were talking about universal gravitation, and I just about got to orbits by the end of class, but the bell was ringing, and I actually made a small mistake, like in the last 30 seconds of class. So here was the last page from your notes. I was talking and trying to explain that equation, and for centrifugal force. You guys know centrifugal force is mv squared over r. That's what you guys figured out empirically from your lab. Okay. I put mv squared over r squared and blah, right? Right. Anyway, if you do mv squared over r, this is the correct result for orbital speed anyway. Okay. Right. You guys go there? All right. So that's some detail. So just in your notes, if you have a square there, just scratch that out or erase it. Or okay. All right. So here's my very ambitious plan for today's 35-minute class. Let's do as much as we can. So I'm going to flip my screen over here. All right, share screen 2. All right, and then let's go back historically, like way back in the day. All right, so since we're talking about gravitation and orbits, actually a lot of the inspiration for physics just in general, like what was Isaac Newton think about when he came up with the laws of motion and was trying to lay down explain the natural world. What a lot of scientists were specifically looking at was astronomy, right? So let's go back thousands of years ago. Right? Now, imagine thousands of years ago, right? Sun goes down and not a lot to do. You can't like read a book. There's no light to read by. You can't watch YouTube videos. Computers haven't been invented yet, but people are like intensely staring at the sky. And thousands of years ago, like people can read the sky the same way you can read a book. You open a book, you see words, your brain immediately processes those and knows what the information means, right? People could look at the sky and say like, oh, well, it's obviously October because the stars would only be in that arrangement, relative to the horizon, blah, blah, it's October, right? So people look at this, and it looks like everything's going around the Earth. Now, what you guys are looking at is called the Ptolemaic model. This is Earth at the center. Here's Mercury and Venus. Here's the Sun, and here's Mars. And it kind of looks like everything's going around us, right? Okay. Now, you guys know what that's not like except the correct model. You may have never seen this before, and that would be a good thing. But that's if you don't know anything about the world or the universe, then that might be your initial thought. The word planet. Do you guys know what language the word planet comes from? How many of you guys are thinking Greek? Yeah, that's what you guys are thinking. Do you guys know what that word means? Translates to planet.
Good morning, Hawk. Happy Friday.
Let me pause this.
We are coming to you live.
All right, recording is resumed. But so the word planet means wanderer, and the reason is because all the stars relative to Earth. Yeah, that's right. Go Hawks! One Friday. So all the stars are so far away that they look fixed relative to each other, right? People didn't know what they were for a long time. They didn't know it's same thing as our sun. Our sun was a star, right? But the planets moved relative to the background stars.
Good morning, Hawk. Sorry for the second announcement. We had a late arrival. Congratulations to all of our fall sports who finished their regular seasons this week. Good luck to golf, bowling, cross country, volleyball, and swim and dive in their post-dive season journey next week. Come out for homecoming game tonight to support our Hawks. The game starts at 7. Tickets will be on sale at all lunches today for $4. Reminder for tomorrow night, you must have your student ID in order to get into the dance tomorrow evening. The dance begins at 7 p.m. and ends at 11. Remember, this is a school-sponsored event, so all rules that apply during the school day also apply at the dance. Have fun and be safe. Please see an administrator today if you have any questions regarding dance rules or the game tomorrow night. And we also want to give a huge shout out to our JROTC for their radar competition last weekend and their collection of items that they have been sending to South Florida. Please continue to bring in items to support the cause as they support South Florida. Have a great day, Vera. Go Hawks.
On Friday. So people are seeing these planets, these wanderers, move relative to the stars, and they don't know what those are. Now, again, at a glance, they just look like really bright stars. The planets do, but people don't know. Right. So they're mapping very precisely where are these objects in the night sky, night by night, year by year, right? And then they notice something really weird about the motion, and you can see it right here. This is Mars. You guys know it's a symbol for Mars, right? Right. So here's Earth that now everything relative to us. Okay? They see Mars. Okay, it's going around. It's going this, and it has this weird retrograde motion. It actually appears to move kind of backwards in the sky, like it's changing direction, and then it goes back to its usual direction. Right. Now you guys know that that's just relative motion, right? As like Earth overtakes Mars, and they're both moving around the sun, right? But people back in the day didn't know this. They didn't think it's about like relative velocity and blah blah blah, right? They didn't have no cars to jump in. They couldn't like go 60 miles an hour and realize that, oh, you can't feel how fast you're going, right? They didn't know that. Right? So what they were able to do is put this together in a mathematical model. Greek guy named Ptolemy, so this is sometimes called the Ptolemaic model, said, okay, well, we can mathematically describe this. We can predict like many years out. I can say 5 years out. I can predict where Mars is going to be exactly in the sky and this weird retrograde motion it does. They didn't have a theoretical reason for that, though. They couldn't explain like why that would be. Well, many thousands of years pass, right? And along comes a guy named Copernicus. And Copernicus says, well, hang on a minute. If you just reorient the system and you take the sun and you put the sun at the middle and have all the planets going around that, then this is a much simpler model, much easier to explain because all the planets could just go around the sun. And here's Earth. Earth is just like one of many planets. And then this explains all that retrograde type motion because it's just relative motion of the planets. Okay? So all fine and good. Maybe some kind of circular orbit. Except that planets don't exactly follow circular orbits. It's really close to circular, but not exactly. So switch my screen back over. Okay. So after Copernicus, the Copernican model is also called heliocentric model, right? Heliocentric, sun center, right? Put the sun center. Okay. All right. So after Copernicus, but before Isaac Newton comes along, there's this guy named Kepler who interprets some very precise data that was kept over many years by another guy, astronomer named Tycho Brahe, and the starting assumption was, well, okay, these orbits are probably circular, right? But if you mapped exactly where in the sky, for example, the planet Mars would be, suppose you took this protractor and put it up against the sky. Could you guys imagine like horizon to other horizon, right? You map exactly where is Mars night by night by night, right? You say, okay, well, if the orbit was circular, here's where Mars would be, blah 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 blah, right? Right. You guys know what 1 degree is, right? It's like one tiny little sliver of little tiny wedge, right? A tiny fraction of that degree was the difference between where Mars would be for a circular orbit and where it actually was empirically observed to be. And that threw everything into commotion. And long story short, Kepler realizes that planets don't actually follow circular orbits. They follow a little bit different shape that I'm going to go over with you guys right now. Do you guys have a string on your desk? Have a string? Okay. Go ahead and tie a loop with the string. I think it gave you guys probably a little bit longer string than you need. So try to get a loop that's it's a little on the small side, but that'll work. Right. It could be a little bit bigger than that. Here's for scale. Yeah. Okay. So I made it kind of small. Actually, I have one from yesterday. Actually, this one's a little bigger. This is mine from yesterday for my other classes. Right. You need 3 pencils to do this activity. This is just for your notes. So if you don't have 3 pencils, sorry, or I have pens. Right? I'm going to put down a couple of marks. Bam, bam. Right. Guys, here's 2 marks. Right. I'm going to hold these 2 pins exactly there, and they're not going to move. Okay. Then I'm going to take my 3rd pen, right, and make a triangle. Hey, look at that. You guys see a triangle shape? You guys see a triangle there? Right. Or wait, what about this triangle? What about this triangle? What about this triangle? I could probably make a lot of different triangles. Look at all these different triangles I could make with these 3 pins. Is that okay? Oh, I could go all the way around, couldn't I? Go all the way around this way. All right. And that right there, guys, what's the name of that shape that I just made? It's not a circle, it's an ellipse. Ellipse. That is an ellipse. Ellipse. Right. And it turns out, to connect this back to the physics and astronomy, that's the actual orbit or orbital path that planets follow. And turns out that you see these 2 points here. You guys probably learned this in a math class, maybe algebra 2. What are these points called? Focal points. Focal point. Focal point. I think the plural is like foci. Right? And the sun is at one of these focal points, or in general, the star, and then the planet's going around it. Right? So here's a star, here's the planet, they go around, right, this elliptical shape. Right? That, by the way, is called Kepler's first law of planetary motion. I think there's a poster hanging up here somewhere. That's Kepler's laws of planetary motion. Right? This is first law. Planets actually go around in ellipses. Right? Now, there's a reason why. I'll come back tell you guys later that you don't see actually circular orbits. Right? Now, do you guys think that as the planet, as the planet's going around, sometimes it's far away from the sun, sometimes it's closer. Do you think it's going constant speed, or do you think it speeds up and slows down? It does. When it's close to the sun, what do you think it's doing? Yeah, it's going really fast. And then over here, it's going a little bit slower, right? Okay. All right, so I'm setting up Kepler's second law of planetary motion, which is, suppose you mark off a certain amount of time, let's say like 30 days. So 30 days, it takes the planet to go from here to here, for example, right? Okay. And then when it's over here, since it's going slower, maybe 30 days is only like from here to here. I'm just making something up, right? So there to there takes 30 days, there to there also takes like 30 days. Okay. Okay. And then if you make like a pizza slice looking wedge, or right. Remember, these are each equal times that the planets move, right? And you look at this area, hashed into area. Do those areas look pretty close to each other? Right. That Kepler said that those areas would be exactly the same. And this was the equal areas and equal times law, right? Now, I think it's crazy that Kepler figured any of this out. But one reason I think it's especially crazy to figure this out is because to me, this looks like a really complicated integral calculus type problem. But this is before Newton comes along, before calculus has ever been put down on paper, right? So I figured this out. All right, and then many years later, Kepler figured out this third law of planetary motion, which relates the time period to the average distance of the planet from the star. Now, of course, that distance changes because sometimes it's a little closer, sometimes further away, right? But the orbits are kind of close to circular. You could take like an average distance. That's what that R is, like radial distance. Okay? So the time period squared is directly proportional to the cube of the distance. So I'll give you guys an example. Suppose there are 2 planets and one planet is twice as far away from the sun as another, right? So you effectively double this R, right? Well, 2 cubed, isn't that 8? And if you take the square root, what's the square root of 8? That's like 2.8. Right? Okay, so the planet that's further out, obviously it's going to take more time to go around the sun. How much more time? Well, if it's twice as far away, it takes 2.8 times the amount of time. Okay, guys see that? All right. Now, what I have right here, Kepler didn't figure this bit out exactly. This is like an updated version when you include Newtonian gravity, right? So Newton comes along later, and then with Newton's laws of physics, you can look back on things like Kepler's third law and say, oh, well, obviously this has to be true, given Newton, and this is like an updated version of that. Okay, so will any of that be on the AP exam? Maybe a little bit, like elliptical orbits, they might reference on the AP exam, but you have to memorize Kepler's laws, probably not. A little bit about ellipses. All right, here's the center of the ellipse. Bam. Do a little more math with you guys, and I'll cut back to the physics. Okay. I'll call these 2 arms A and B. Well, there's some mathematical name. I forgot to look it up. Okay. Does anybody know what these arms of the ellipse are called? The short arm and the long arm? But whatever. Right. That's just definition stuff. Okay. Can I make a rectangle with these? And when the area of that rectangle be A times B, right? Guess that rectangle. Okay. How many of those rectangles do you think would take to fill the area of the ellipse? Let's see, well, if it was 4, bam, 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 bam. I've got this excess here. Right, so it has to be less than 4, right? What do you think?
Would be pi.
Pi. Nailed it. Right. So the area of an ellipse is pi times that rectangle, which is AB. Do you guys see if you take these 2 focal points and put them right on top of each other, you get a circle? Do you think a circle is a special kind of ellipse, just like a square is a special kind of rectangle? In that case, wouldn't the area be pi r squared? Sure would be, wouldn't it? Okay. Another question for you guys. This one's a little trickier, right? The distance that the planet goes around, that could be the perimeter, right? Does anybody know what the formula is for the perimeter of an ellipse? Well, that's a trick question. The answer is no. Right? Nobody knows. That is an unsolved mathematical mystery. So enjoy that. What's next? All right, so yesterday, you guys learned some new stuff, and we were looking at universal gravity. Here's some new stuff that you guys learned. Right, you guys learned that if you have the two asteroids or a planet and a moon, I'll label this capital M and lowercase m. Some textbooks do m sub 1, m sub 2. Right, and they're separated by some distance. Right, call that distance. I'm going to call it r because maybe one is orbiting the other with some radial distance, right? Or I set up another model that's effectively the same, but it just looks a little different, right? What if you're standing on the surface of a planet, right, with some radius that I'm going to call capital R, like the fixed radius of a planet. Right? Now the planet can have mass capital M, you could have mass little m, and it's physically the same because you're gonna. I forgot to emphasize this point yesterday, but notice this distance between the two. It's not a surface to surface distance. It's a center to center distance. You guys see that? Center to center. We're going to treat each of these masses as if all the mass is located at a single point right at the center of mass. You guys see it center to center? Okay, and if that's true, then right, this is just a specialized version of this. Right? You guys see that? Okay. Right. And what you guys learned is that the gravity force of attraction between these two, also the attraction here, right? It's equal and opposite force. Let's label that real fast. It's worth it. The time here. Force, and it's an equal magnitude, opposite direction force. Okay. Force. Right. You pull up on the Earth as much as the Earth pulls down on you. Same force. Okay. That force is equal to universal gravity constant, which is a tiny, tiny number, times each mass multiplied together, divided by the distance squared. Right. Then I said. So that's in general, that works for both of these models. Right? But if you look at this planet model specifically, say like, what is the gravity field at the surface? Okay, if you just divide by the person's mass, you can get the gravity field, which is Gm over r squared. Looks like that, right? And then right as the bell was ringing, I was trying to derive this, but sort of ran out of time, so I'll rederive this with you guys today. But here's just cut to the answer: the orbital speed. So if you like you blasted a cannonball up to the side, that was Newton's thought experiment. What if you were on a really tall mountain, you blasted a cannonball up to the side? How fast would you have to go to like constantly fall around the Earth? Right, so it's like falling around the curvature of the Earth. Right, that'd be orbital speed. Right, here's what the answer ends up being: square root g m on r. Now that's for a circular orbit. Right, that's to say a circular orbit. Now you guys know a few minutes ago I told you that nothing really planets don't move in circles around stars. They actually move in ellipses. Right, but here, one thing at a time here. Hold on to the idea because then we're gonna come back to that. Right? All right, guys, so far. All right. Now what I focused on, because the AP focuses on this, higher level thinking focuses on this. Right? It's like proportional relationships. So like if you double the distance, guys, if these two objects double the distance, what happens to the force between them? Becomes a quarter as much, right? Because factor of 2 squared is 1 over that 1/4. So double the distance, you get a quarter of the force. We did that yesterday, right? Right. And so that's more like what you guys are thinking. But what I really need to do just to fill in the gaps is to just do some traditional plug and chug. So let's do that just to cover our bases. Okay. We're going to calculate some of the stuff. We're going to calculate this one, then I'll rederive this, and then we'll do a calculation here. Okay. So let's do a plug and chug for this guy. Okay. So here's the model we're following. Right. Gravity field is universal gravity constant times the mass of the planet divided by radius of the planet squared. Okay. Okay. Let me give you guys some numbers. Here's the mass of Earth. Mass of Earth is 5.97 times 10 to the 24 kilograms. You guys know that's 5970000, just a crazy string of zeros, right? Right. Okay. It's a scientific notation, right? The radius of the Earth is it's about 6 million meters. Here's the number spelled out long form, right? And here it is in scientific notation. Okay, if you need to review scientific notation, okay, 10 to the 6 is a million, right? Side note here, let me make a long overdue correction. Did I do this with you guys yesterday? Tell you guys that. Okay. right? So that comes from the property of the Earth. Right? If you go from the North Pole to the equator, that's 10 million meters around the curve. Okay, that corresponds to those being the radius there. Okay, so you guys got it. Okay, universal gravity constant is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Right, which here's expanded form just in case you need to see it. Newton meters squared per kilogram squared, right, like that. Okay, so we got these numbers, right? Let's just do some straight plug and chug and see what is the gravity field at the surface of Earth, which is something that you guys already know. So you already know the answer to this question, right? What does the answer have to be? 9.8 meters per second squared. Right? Let's see if that's true. Right. Let's get calculator practice anyway. Right. So we're gonna go. The gravity field is fraction bar. 6.67 times 10 to the negative 11. Now, I'm going to take the units and just move them out here. It's going to be either Newton per kilogram or meter per second squared, which are equivalent ideas. Right, at the end. So I'll just put the numbers in the fraction. So GM, mass of Earth, 5.97 times 10 to the 24 of those kilograms. Here's 1 kilogram. Right, yeah, 10 to the 24 of those. Right. And then radius of Earth. I'll do scientific notation. 6.37 times 10 to the 6. 10 to the 6 is a million. Right. Don't forget to square that. Right. Here's good calculator practice. I think you guys will probably be pretty good, but yeah, just do a run through. Just make sure you can plug this in correctly. Right. Because there's a negative, an exponent, there's parentheses, there's dividing by, there's powers all over the place. Right. Want to make sure you get the order of operations correct. Right. Right. So open parenthesis. 6.67 times 10, right? Caret can do power. Right? There's 2 subtract signs on there's 2 minus signs. One is for subtraction. Don't do that one. Choose the one on the bottom, which is a negative sign. That's if you have this model calculator, right? Every calculator is a little bit different. Let's try to have this one. Right. So there we go, like that. Close open, that will automatically multiply. 5.97 times 10 to the power 24. Close, divide by, open. 6.37 times 10 to the power 6, close, square, right? Right, now that should do it for me. Right, let's see if we get 9.8 meters per second squared. Bam! It is 9.8. It looks like I have 3 sig figs on each of these, so maybe I could even say 9.81 meters per second squared. Okay. There you go. Right, is that okay? You guys are right? All right. Let's do. Right, you guys ready for the next one? Right, let's do orbital speed. Now, this I was trying to drive you guys, and the bell was chasing us out, so I have to go back and redrive this. Okay? Take a look at this planet. Right? Suppose I got well, this is going to be a satellite. Now, satellite, there are different orbital levels you can have, but a really common one is what's called low Earth orbit, which is only about 400 kilometers up. Did I tell you guys that if Earth was the size of the basketball, size of a basketball, and you wrapped it in just like that plastic wrap, right? That could pretty well represent the thickness of our atmosphere, right? So our atmosphere is not very thick in the big scheme of things, right? Right. So 400 kilometers up, 400 kilometers compared to 6 million meters, right? Is that's it's a fraction, right? This low Earth orbit is not too far from what I've drawn. Actually, might even closer to the planet. Okay? So how fast do you have to get this going to the side? I'll call it the orb. Right. So it stays in a circular orbit around the Earth, right? Right. So I would say that this satellite has 1 force acting on it. And so if I make a free body diagram for the satellite, isn't just its weight? I'll do F sub G, right? Its weight is pulling it down. Right? Right. Now we're going to combine the idea with your last lab and say that, well, that in this case, gravity force is acting as the centripetal force holding it in a circular path, right? Right. So I'm going to say the centripetal force is provided by the gravity force, right? And centripetal force, the expression you guys have is mv squared over r, okay? And gravity force, you guys have an expression that goes gmm over r squared, right? Good so far? Right. I just see one of the r's I can cross out. R doesn't completely cancel, but perfect, right? Now, one of these m's canceled. Now the big M is the mass of the planet, the little m is the mass of the satellite. Right? The fact that that cancels out, what that means in physics terms is that it doesn't matter how massive it is, you're ultimately going to get the same value for the orbital speed. So if I'm in the International Space Station, I step outside for a spacewalk and I hold this out and I let it go. This object in the International Space Station could go side by side all the way around because they need the same speed to keep in orbit. Okay? And that speed is, if you just square root both sides, the orbital for a circular orbit, say circular, is the square root of gm on r, just like that. Okay. Now, I think it's a good idea to keep this formula in your back pocket, especially if you're like good at memorization. This could definitely pop up on the AP exam, but if it does, especially if it's an FRQ, they would expect you to derive this from scratch, right? So if orbital velocity shows up on an FRQ, write this, then write this line, then write this line, and that might be check like 2 or 3 points. Right? If you just write this, there's a good chance they're gonna say like no, or not give you points or something, right? Or not give you this point. All right, well, let's try this out. Let's do a little just standard plug and chug. Let's see what the orbital speed is around Earth at low Earth orbit. The orbital for Earth. Right? Every planet's going to be a little different, right? Do you guys know the first artificial satellite that was sent into space? Sputnik, yeah, sent up by the Soviet Union. Kicked off the space race because everybody here freaked out, like, oh shoot, the Soviet Union is going to like start dropping bombs on us or something. Right, so we had to come up with their own space program. That was in 1957. So everybody was trying to do this exact calculation we're doing right here. Like, how fast do we have to send it to keep it in orbit? Okay. So we got 6.67 times 10 to the negative 11. We got the mass of Earth, 5.97 times 10 to the 24. That's kilograms. I'm going to do the same thing I did before. I'm just going to pull the unit out. It's ultimately going to be meters per second. Radius of Earth, 6.37 times 10 to the 6. Like that. All right, let's try this out. So square root. Now here's a calculator trick. There's a few ways to do this. One way is you could calculate all the stuff on the inside and just do the square root after the fact. I'm going to do it all in one go. But if you do it all in one go, you have to be careful because see how this calculator gives me a parenthesis to start with. As soon as that parenthesis closes, it stops square rooting. Okay? But clearly everything's being square rooted. So here's a trick around that. Just open up a ridiculous number of parentheses, and then it's never going to stop square rooting. Right? That's just one trick. Okay. 6.67 times 10 to the power negative 11, close open. 5.97 times 10 to the power 24, close, divide by open. 6.37 times 10 to the power 6, close. Okay. And bam, right there. So orbital speed around Earth. Now this is only true for Earth. Okay, so low Earth orbit is pretty close to this number, 7906 meters per second. Okay. Okay. You get going that speed around Earth. Okay. You guys do see 400 kilometers up and just fudging a little bit and saying that's approximately the radius there because the big scheme of things, it's only a few percentage points different. Actually, the gravity field up there is about 90% of what it is down here on the surface. So it's pretty close. Okay. So here's the thing. This is for a circular orbit. That means if you went any slower, if you went like 7,800 meters per second, what would your satellite do? Yeah, it would fall. It would go and crash down to the ground, or like spiral down and crash down to the ground. Okay. So this is a really fragile scenario, isn't it? Okay. In fact, when the solar system was forming 4.5 billion years ago, if there was anything that was in a perfect circular orbit around the sun, that would be really fragile. And then if like Jupiter swings by and like goes a little perturbation, then well, it's gone. It's just going to spiral into the sun. And then 4.5 billion years later, we're not going to see it. Hence we don't see any planets with perfectly circular orbits. You know what would be safer is if you bump the speed up just a little bit. What if you're like 8,000 or 9,000 meters per second? Right? Now that won't be a circular orbit, but guess what kind of orbit it's going to be? Ellipse. Bam. Right? Now you can keep going faster, faster, faster. You guys know comets. Comets go like beyond Pluto and they go real close to the sun and swing by. Right? They have crazy, highly elliptical orbits. Comets do. Right? Planets are pretty close to circular, but comets are highly elliptical. Right? But still an ellipse. Right? But at some point you can go so fast that you reach what's called escape speed. Escape speed is up here. I'll tell you guys what it is, and this is going to come back later. The escape ends up being square root of 2gm on r. I can prove that when we get to conservation of energy. Okay. So it's the square root of 2 times this, which is about 11,200 some meters per second. Right? If you hit this speed going away from Earth, you could cut off the engines and you'd be going fast enough that you could fly away forever. From the Earth anyway. All right, you guys got it? All right. Okay, there's a lot of stuff I want to do. I've only got a few minutes left. I'm gonna have to say some of the stuff for next week. But guys, what are you gonna do over the weekend? AP Classroom Unit 3? You're gonna do that, right? AP Classroom Unit 3? Let me throw you guys a few hints before the bell kicks us out. Okay. One is there are a couple of questions about 4 fundamental forces. Let me jot this down real fast. So there's gravity, okay. There's electromagnetism, and then there are 2 nuclear forces called the strong and the weak force. Right. And each of these forces has a different strength and that nuclear acts over a different range. Okay. The top 2 are the ones we mainly care about in this class, right? Gravity, like attractive force. Right? By the way, if you get to graduate level physics, then they actually turn this on its head and say, well, it's not really a force, it's actually an artifact of the curvature of space-time, but we're going to ignore that, just call it a force. Okay? Electromagnetism, this is the force that's responsible for almost everything else, just electrons pushing against electrons. Is there a normal force from my hand on this pen? Yep. Is it electrons against electrons? Bam, it's this category here. These guys are nuclear forces. They only act like within the nucleus of an atom. So there are a couple questions about that. I think you guys will be able to figure that out with the context I just gave you. Another thing, there is a question about a ball on a string in a circular motion, but it's going in a vertical circle. Now, guys, do you think it's going in a if this was horizontal, if you're looking down from a helicopter, horizontal, do you think the ball could be constant speed all the way around? Yeah, you would expect it to be. But if it's vertical, do you think it would be speeding up on the way down and slowing down on the way up? You would expect that too, right? Now, here's the thing. One of the last questions that you guys are going to get involves that. It's like the ball speeds up on the way down, slows down on the way up, which would be what you expect, right? But there is a question, like somewhere in the middle, where they give you the scenario for a vertical circle, where they tell you, as a simplifying assumption, that the ball goes a constant speed all the way around. Now, that's a huge simplification, wouldn't it be? Right? But the question that they end up asking about that ends up making it a lot easier to solve. I guess they could be approximately true if you swing around really fast, proportionally wouldn't change a whole lot. Okay. But here's the thing, guys, this ball, okay, do you think that this ball has a tension force acting down here, force due to tension, and also a force due to gravity? Right? They're both pulling down that way. But when it's down here, do you think it's the same force due to gravity, but probably a huge force due to tension down here, right? And the sum of these is the net force. The sum of these is the net force. And I bet you could figure out some triple force based on that. All right, I think you guys got that. I will see you guys on Monday, and we'll go over AP Classroom on Monday. All right, you guys have a great weekend.